Okay, this is a quick video on notes part 3. This is Le Chatelier's principle. Henri Le Chatelier was a French chemist who had some ideas about equilibrium. Remember, in equilibrium, reactions are going forward and backwards at the same speed and the same time. So with equilibrium shift, if we put a stress on a system at equilibrium, like say we have a glass container filled with two gases that are reacting back and forth at equilibrium, um, if we stress out a system like heating it up or increasing the pressure or anything like that, it will cause one of the reactions to go faster for a while than the other. And then eventually the rates will again become equal and equilibrium will be reestablished. So that's Le Chatelier's principle. Okay, so if you have a shift to the right, just to get the terminology down here, a shift to the right involves the forward reaction going faster for a while. So let's say that we put N2H2 and ammonia, and we have those guys in a container. If we get the N2 and the H2 going faster for a while, that's a forward reaction going faster. It's also known as a shift to the right. Okay. If we have a shift to the left, we're saying that the reverse reaction is going faster for a while. So we're looking at this one going faster. So that means that ammonia would be decomposing faster than it's formed if we have a shift to the left. Again, this happens if we do something to the system, like increasing the temperature. Okay, so Le Chatelier's principle, just stated simply, is when an equilibrium system is subjected to a stress, the system shifts to relieve that stress. So we can control reversible reactions that are in equilibrium by doing things to them, by adding stresses to them. Okay, so here's an example of Smog in Bakersfield, California. You'd also see this in Los Angeles, and this is a kind of a pertinent topic right now because NO2 in the air has been going down while we're in this quarantine time because there's less people driving their cars, which put out NO2. Well, NO2 will naturally form N2O4, dinitrogen tetroxide, and N2O4 will reverse and form NO2. Okay, so one way to get it to go towards the right side is to decrease the heat. So if I take heat and take it out of there, it makes it go that way a little bit faster. Now, a couple of things about NO2 gas. NO2 is a brown color. Just put BRN. And N2O4 is clear. It's colorless. So on a cooler day, if we're taking heat out, it's going to shift that way, and we're going to get air that's a little bit clearer looking than we do the brown that we see when there's a lot of NO2 in the air. So we've got that equilibrium going on up in the atmosphere that can be controlled by temperature and pressure as well, as we'll see. So let's look at some rules here for Le Chatelier's principle. If you add a substance to the container, and you got to remember all of these things are in the container at one time, there's reactions going back and forth in there. The reaction using up a substance is favored. Okay, so let me put it this way. If I put more N2 into this thing, it wants to get rid of the N2 that I added to it. It wants to use it up because I added extra. And so when that happens, it's going to shift to the right. Now, consequently, if I add NH3 or ammonia to the system, it wants to use that up, and it would shift to the left to get rid of it because that's the reaction that gets rid of it. So by adding substances, we can get it to shift in one direction or the other. Okay, just remember this little thing to remember it by. If I add it to the left, it shifts to the right. If I add it to the right side, it shifts to the left. It does the opposite. Okay, so just keep that in mind. So the example we just used, adding N2 will produce more NH3, more ammonia. Okay. If you remove a substance, this is the opposite of the previous slide, the reaction producing the substance is favored. So let's say that, well, let's look at our example here. If we take ammonia and we pipe it out of the reaction vessel, the glass flask, whatever we're running this thing in, if I pump that out of there, these guys are going to shift into overdrive and start making more ammonia to make up for the loss. So they see, quote unquote, that the ammonia is leaving and they react faster to make up for it. Okay, now I wrote chickens down at the bottom because if you take the eggs away from a chicken that's laid eggs, that chicken's going to make more to make up for the loss. And the same thing is true in these. If I remove N2 or H2 from this side, it's going to shift in that direction to make more of it. Okay, so that's how those guys operate. Okay, now let's talk about reducing volume. If I reduce the volume, that equals higher pressure. And if I increase the volume, that equals lower pressure. So the bigger the volume you have, the more room for gases to move around in and their pressure decreases. Go back to gases and remember that when molecules hit each other, it causes pressure, or they hit the container. If the container's bigger, they hit each other less pressure. So if I increase the pressure, the reaction producing fewer molecules is favored. So here's how we have this. You guys have been balancing equations for quite a while now. If I add up the 1 and 3, that's a total of 4 molecules on the left side of those arrows. And if I look at this, there's nothing else over here. I have 2 molecules on that side. So if I increase the pressure, and that's usually by, we have a cylinder, say, with the reaction going on inside of it. And if we have a piston that we can push in and make the volume smaller, say going to there, that's going to cause this reaction to go faster because 2 molecules takes up less space than 4 molecules does. Okay, 2 molecules takes up less space than 4 molecules. So if I make that volume smaller, like I did in this example, I'm going to get it to shift to the right and make more ammonia. This is what Fritz Haber did to make more ammonia to make his explosives and fertilizers. He increased the pressure to 200 ATMs. That's 200 times the normal atmospheric pressure by basically using a piston inside of a cylinder. On top of that, he heated it up and added catalyst and stuff like that we look at. So increasing the pressure, it'll go to that side. And again, there's 4 molecules on the reactant side, this side, and on the right side, there's only 2. Okay, if we do the opposite, it's going to do the opposite. So if I decrease the pressure, let's say we've got our piston and our cylinder and we make the volume bigger. If the volume goes up, the pressure goes down. Okay, they're inverse. Just remember Boyle's law from gases. Okay, so in that case, if I do that, it's going to shift to go to that side because it has 4 molecules. It can take up all the space. So, it's like in our rooms at school, we don't want to be as close together as we can. We're going to spread out the chairs in the room to take up as much space as possible. If the room's bigger, we could spread out even more. Okay, so the same thing's true for gases in a container like that at equilibrium. Okay, if you look at, real quick, this one, this is a special case where I've got 2 molecules on that side and 2 on that side, so pressure will have no effect. So always count up the molecules on both sides. If they're the same like this, pressure will have no effect. So just keep that in mind. Okay, temperature. If you increase the temperature, which is adding heat, the reaction using up the heat is favored. That's the endothermic reaction. For every endothermic forward or reverse reaction, the opposite is going to be exo. And if we decrease the temperature, taking heat away, that reaction giving off heat is favored, the exothermic. So let's look at an example. If we add heat and the heat's on the right side, it's going to shift left. Okay, so that reaction will go to the left and produce more of those guys. Okay, if I take heat away, the reaction going that way is going to shift. It's going to shift forward in this case, which is a shift to the right. So treat it like a substance. If earlier in this video I said if you add a reactant, it shifts that way. If I take a reactant away, it shifts the other way. Okay, so if I add heat's on this side, it's going to go that way to get rid of the heat that I added to it. Okay. All right, let's go to the next example. Again, if we do the opposite and remove this heat and take it out of there, it's going to shift to the right. So anytime you remove something, it shifts towards the side you removed it from. Anytime you add something, like we said earlier, it shifts in the opposite direction. Okay. Catalysts will speed up the forward and the reverse reactions equally. There will be no shift. It will get to equilibrium faster if it's not already there, but there will be no shift in that. So let's look at an example, okay? And it says, which way will equilibrium shift if we do the following things? So if you want to try this out and see if you've got it, pause this now and then come back and check your answers. Okay, so let's look at number one. If we add phosphorus pentachloride, which is PCl5, if I add this, I'm adding a substance, it's going to shift in the opposite direction. So I will get a shift to the right in this case. Okay. If I remove chlorine gas, Cl2, remember, if you remove something, it shifts towards the side from which you removed it. So that's also going to be a shift to the right in this case. Okay. Let's look at cooling the system down. All right, I'm going to use a different color here. If I cool the system down, that's like removing heat. And if I remove heat, it's going to shift to the left in this example. Again, we have to go example by example, look at where it's at, and then figure out what's going to happen to it. Okay. If I heated the system up, it would shift in the other direction. Okay. And then if we increase the pressure, let's look at that and figure out how we can get that figured out. Let's look at the pressure situation. I've got one molecule on the left and I have two molecules on the right. If I increase the pressure, it wants to shift towards the side with fewer molecules because they take up less space. So that's going to be a shift to the left. The last one is if we add a catalyst, what's going to happen? Catalyst will cause no shift to occur. Okay, so we'll give you some examples in an assignment this week to try out for Le Chatelier's principle. And we'll talk about this tomorrow at our Google Meet if you have questions. Okay, so go through this video, look at the notes, and we'll talk about this tomorrow. Talk to you guys soon.